Hey there, in this video we're going to talk about how we can fit a power law to our data. Power law takes the form ax to the power b. And a and b can be floating point values. They don't have to be integers. They can be positive, they can be negative. And this covers an awful lot of physical laws, like the law of gravity, for example, is 1 on r squared. So that's a b equals -2 type power law. And even though power laws are not linear, at least in general, they're not linear, we can still use a linear least squares fit to solve for the coefficients a and b given some data. The trick we're going to use is we're going to take the logarithm of both sides of our equation. So on the left-hand side, I'll have natural log f, and on the right-hand side, I'd have natural log a plus the natural log of x to the b. So I'm using a property of natural logs here, where the natural log of a times b is the same thing as the natural log a plus natural log b. Furthermore, the natural log of x to the b is equal to b times the natural log of x. So we can write this now as natural log f equals natural log a plus b natural log x. And this is equivalent to the equation of a line. So if we think about our x and y variables being natural log x is the equivalent of our x, natural log f is the equivalent of our y, then b is the slope of that line, and then natural log a is the intercept. And then all we have to do is untransform. So we do the natural log of everything first, do a linear least squares fit in log space, and then once we've solved the linear least squares problem, we transform back to get what our power law is, with the slope of the line corresponding to the power in the power law. So back in the notebook here, let's try fitting a power law. I think a good power law to do would be the Stefan-Boltzmann law. So Stefan-Boltzmann law tells us that luminosity is, let's do this as an equation. Luminosity is equal to sigma t to the fourth. Where sigma is the Stefan-Boltzmann constant, has a value of 5.67 times 10 to the -8. So let's try and fit and see if we can recreate the Stefan-Boltzmann law, and so like the sigma and the t, given some made-up data here. So first, we're going to create data based around a perfect version of the Stefan-Boltzmann law, and then we're going to add some errors onto it using random numbers. So for sigma, 5.67, 10 to the -8. For our temperatures, let's use a linspace. 1 to 100 with 100 steps. For our error, let's go 2% error in temperature. So to recreate a 2% error in temperature, I'm going to take 0.02 times the temperature and then multiply that by normally distributed random numbers. So we'll do np.random.randn, and we need 100 of those random numbers. Okay, and so this is going to give us values with a standard deviation of 0.2, a little bit higher, a little bit lower than the actual temperature. And then we can calculate our noisy luminosity. So this would represent something we'd measure in an experiment as sigma times t plus the error to the fourth. And let's just plot that to see what it looks like. So we're going to plot t, l, we'll do red dots, we'll do little dots this time, and plot.show. Okay, so there's our data. And you can see, it looks like the error is worse up here for bigger numbers, but that's just because 2% of a bigger number is bigger. Now, data like this is what we would call a power law, or it could be a power law. You see this kind of shape, it could be a power law. How do you check? Well, if you plot on logarithmic axes, if it's a straight line, then it's a power law. So the way we can make a logarithmic plot here in Python is using not plot, but instead log-log. And log-log acts just like plot, but with log scaling. There's other ways to force the log scaling, but this is your fastest way to do it. So what we're going to plot here is temperature, luminosity, and we're going to use red dots just like we did before. Let's show it. So it looks like this is pretty much a straight line. Now you'll notice it looks like the spacing between the points has changed. That's because we've changed the scaling on our axes. So this was literally linearly spaced points using a linspace. There's also a log space, and so we could have uniformly spaced points on this plot. But that's not the point right now. The point was we had some function to start with, and I want to use some tricks here to fit to least squares fit the power law itself. Something else I want to show you here is if we turn on a grid, the idea here with the power law is that the slope is the power. And so if we count here, so like down here, we're going to go one grid step in the x direction, and in the y direction, we went from, this would be like almost -7 to around -3. Hey, that looks like it's steps of 4 grid. So 4 divided by 1 is 4. The slope of this is 4. It's to the 4th power. And so we're going to basically just automate finding the slope of this thing to find the power in the power law. So to go along with what we did by hand just a little while ago, we want to take the logarithm of our data. So natural log of t is literally the log of t. Natural log of the luminosity will be log L. And then we can do a polyfit. So we're going to have, in this case, B and the natural log of A come out of this. Remember, we're doing a power law of the form A times x to the B, so, or A times t to the B in this case. So B here is going to be our power, and natural log of A is that coefficient out front. And what we're going to polyfit here is natural log t is our x values, natural log L is our y values, and we want to do this to first order because we're fitting a line to the logarithmic data. So our original function, was, you know what, let me just put that in a comment, just so we have something to look at. So our original function here is of the form a times t to the b. Okay, so to get a, having done the polyfit, we have to turn this natural log back into the original function, and the reverse operation of a log is an exponential. So we'll take the natural log of a and exponentiate it to get a. B is already in the form b. We don't have to do anything to that. And so let's print our results here. We'll do power here. That's the b. We'll do that to 2 decimal places. And the Stefan-Boltzmann constant, that was the a that we had here. And we'll do that to 2 decimal places. Okay, so that should plot the results of the Stefan-Boltzmann law, at least if I remember my quotes. I think actually like 3 for 3. I've left off that last quote. All right, and the power is 4 and the sigma is 0. Is that right? Well, I guess it's actually just really tiny. The power, of course, is 4. The Stefan-Boltzmann constant is 10 to the -8. So printing it to 2 decimal places, that was kind of a dumb thing to do. Let's print it as an exponential. So that's 2 decimal places in scientific notation. There we go. So 5.67, 5.6, because we have noisy data. Looks pretty good. And let's try plotting this just to make sure it's a good fit. So I'm going to go back to my original plot. T, L, and we had red dots, and then on top of that I want to plot my fit. So that would be T, A times T to the B, and we'll do that as a black line. Show the plot, and look at that, we've got this nice fit. Okay, so that's your common go-to trick to fit a power law and to figure out what the power and the coefficient out front is. Now, I guess one warning I should share with you with this approach, since we are transforming to log space in back, is what happens is it puts a little bit more emphasis on the smaller points here. So these have more of an effect on your fit than the points out here. So depending on the quality of your data, that might lead to a curve that looks like it just completely misses the points that are larger values because it weights these more. In some sense, it's just because there's more of them. So do be aware of that. That is something that can go wrong, in which case you might want to fit just some of your data. Like if you really only care about temperatures above 60, you might want to just start your fit here at 60. Of course, having less points means your fit's a little bit less certain. It's all trade-offs, so real world can be a little bit more messy than what I'm showing you here, but nonetheless, this is the basics of your techniques for fitting data.